Okay, so I know everyone in the room is very familiar with this area, but these talks are being recorded, so let me just start at the beginning. So the threesome problem is you're given a set of n numbers, and you want to know are there a and b and c such that a plus b equals c. And it comes in lots of different variants that aren't substantively different. You can say maybe a, b, and c have to be distinct. You can say maybe a, b, and c come from their own sets, capitals A, B, and C. But they're all essentially equivalent. Okay, so if you want to simulate being an undergrad these days on the job circuit, you can try to come up with an n squared algorithm in like 2 minutes, which is what you're expected to do at very good, Bay Area companies, I think, maybe 5 years ago. It's probably, out of date by now. But anyway, it is possible to come up with an n squared algorithm with completely elementary observations about the problem. And the job interviews usually don't distinguish between A being a set of reals, where you manipulate it with comparisons and additions, and A being a set of integers, where you can manipulate it with other natural operations on integers. But the problem does have two kind of natural variants. So the strong threesome conjecture from the 90s is that the job interview algorithm that you came up with is optimal. It's n squared time, and there's even stronger conjecture that the number of numerical operations that you need to solve the problem is also n squared. And there's some circumstantial evidence for this in the 90s. Okay, so the strong threesome conjecture is too strong, but it might still be useful. So there's some weak refutations that say that the strong threesome conjecture is not literally true, but maybe spiritually true. So it's not literally true because you can beat n squared by a smidge. So Baran, Demain, and Petrovsky showed that you can beat it by a roughly log n squared factor when the input is integers. This is randomized. Fox last year, we showed you can do it with n to the 3/2 comparisons, a lot of time, but n to the 3/2 comparisons, and you can shave about a log n factor off when the input is reals. Okay, so given that there's weak refutations, the modern threesome conjecture, I'll call it, is that you can't beat the exponent 2. You can beat it by some lower order additive term. Okay. I'm sorry, I didn't hear about the drinking rule when I came in. So. It's okay. This is the first drink. True story. So when my wife heard that I was working on the threesome problem, she told me in so many words that this is a constant time solvable problem because the answer is always no. So she didn't appreciate this. But if you're open-minded, if you're open to new experiences, there's subquadratic algorithms out there. Okay. So when Lassie Babai's big announcement about graph isomorphism came out, people were always like, oh, immediately afterward they said, we always knew this was going to be the case because there was no hard distribution. It seems a little strange, the timing, but they always said, if you don't have a hard distribution when you come up with a hardness conjecture, there's something very suspect about it. So as soon as you give a hardness conjecture about a problem, you're probably obliged to immediately come up with a hard distribution and say, beat this first, and then we can talk about the general problem. So here's a hard distribution, as far as we know, for threesome. Pick A, B, and C uniformly at random from the first n squared integers. And you're going to have threesome witnesses all over the place. So then filter out every element of C that's involved in a threesome witness. And whatever remains is your instance. And you can leave one witness in there if you want it to be a positive instance. And if you don't like the filtering step because that takes too much time to actually generate something from this distribution, you can just pick A, B, and C from the range 1 to n cubed. And then you'll have a constant number of threesome witnesses in expectation, and finding one as far as we know is hard. So if you want to look at a special case of threesome, look at randomized instances. Okay, so here's a brief review of how threesome was used in geometry, mostly in the 90s. Basically, you have this set of n numbers, and you manipulate the inputs with linear transformations. And a lot of times the reductions are almost completely trivial. Like for, let's say, a robot manipulation problem, you could create 3 infinite lines corresponding to the sets A, B, and C, put little gaps in those lines, break them up, corresponding to which numbers are in the sets A, B, and C, and say you have a robot that's really, really long and really, really, really skinny. Say it's a line. And then you just show that the only way you could possibly get the robot from above the first line to below the third line is if there was a threesome witness in the original set. Okay, so reductions of this flavor were very common in the 90s. Okay. So one thing that I want to emphasize in this talk is that the threesome conjecture is it's at one end of the spectrum, which is what is the largest running time that we can state with a straight face. And a different way to look at it is what is the weakest threesome type conjecture that is still useful. So in this case, the weakest useful conjecture that you can come up with is that threesome just takes superlinear time. This is the weakest conjecture that you can come up with that gives you some kind of non-trivial results, because you had input complexity n and you created some geometric instance with complexity n, so any superlinear lower bound transfers back to the original problem. Okay, so Petrovsky took a very sharp departure from the algebraic reductions. And to explain what Petrovsky did, I have to introduce a few more problems, because the threesome problem wasn't perfectly suited to what he was doing. So threesome is given a set of n numbers, find a, b, and c, such that a plus b equals c. Convolution threesome is, this is not a good interview question. Find a quadratic time algorithm for convolution threesome, because it's obviously quadratic. So you're given an array of numbers, and you want to find indices I and j such that ai plus aj equals ai plus j. Okay, so he's going to reduce threesome to convolution threesome, and he's going to reduce convolution threesome to set disjointness. So set disjointness is we're given a set system A over a universe U, and some queries which are pairs of sets, and we want to know for each query pair AB, does set A intersect set B or not? So there's no obligation to find a witness, but it's just a yes or no question. So set disjointness is, it's a sort of a decision variant, and the reporting version of set disjointness is the input is identical, but when you're given the query, you have to explicitly enumerate in some arbitrary order the elements in the intersection of A and B. Okay, so these are Petrovsky's reductions. So the first reduction is to get from integer threesome to integer convolution threesome. And basically what he shows is that given any parameter k, there's some overhead of n squared over k, and then the reduction makes roughly k cubed calls to a convolution threesome algorithm. So the right choice of k in this case depends on the actual complexity of convolution threesome, and you have to hypothesize what that would be and then work backwards and pick the optimum k. So Petrovsky didn't have this in there, but there's a minor error in his paper, but you need a few more calls to avoid witnesses of a certain type that he didn't want. Okay, so once you have convolution threesome, you can reduce that to a set disjointness instance. So this set disjointness instance has a universe of size n. The number of sets is n to the 1/2 plus epsilon. Epsilon is a parameter you get to pick. And q, the number of queries, is n to the 1 plus epsilon, same parameter. And regardless of what epsilon you pick, the input size is n to the 1.5. So the epsilon that you're allowed to pick is not completely arbitrary. So it depends on the complexity of convolution threesome, and if everything is quadratic the way we think it is, epsilon can be between 1/2 and 1. So the point of this slide is to illustrate a few weaknesses in Petrovsky's reduction. The first is that you have no control over the output size. It's always n to the 1.5, regardless of how you choose any parameters. So you can't really create instances of arbitrary, types. The second is that epsilon has to be between 1/2 and 1, so which means that the number of queries is n to the 1.5, which means that the highest lower bound that you could possibly expect per query is square root of n, square root of little n. Okay, and the third problem is that there's a certain amount of loss that gets introduced in all of these reductions. So you lose something going from integer threesome to convolution threesome, and you lose a little bit more going to set disjointness. And what I talked about earlier, the weakest useful threesome hypothesis is actually not really strong. So, for example, you're bound on n to the epsilon here. You need a gap between this lower bound and this upper bound for you to be able to pick any n to the epsilon at all. And the only way that this gap is non-empty is if convolution threesome is, the exponent is at least 5/3. Okay, so then you work back and you say, well, what happens if we put n to the 5/3 up here and then chose the optimum k and figured out which running time for threesome that we would get? We would get, oh, AT&T Wi-Fi, okay. If you work backwards from there, you'd say, well, if the exponent for convolution threesome is 5/3, then the exponent for threesome would be 13/7, and that's basically the threshold at which you get any non-trivial result. So if someone came along and you only had these two reductions and someone gave you an n to the 13/7 threesome algorithm, everything could just hypothetically unravel. Okay, so we're going to basically, we're going to use all the tools that Mihai used. We're going to use them in a different order and assemble a reduction directly from threesome to set disjointness and set intersection and get stronger results. So we're going to get higher lower bounds, and we're also going to get higher lower bounds from a weaker threesome conjecture. So whereas here, the weakest useful conjecture had this exponent 13/7. We're going to get this weakest useful conjecture down to n to the 1.5. Okay, so we have, let's say, 3 input arrays A, B, and C. To see why this threesome just really naturally fits a set intersection, set disjointness framework, you can say, suppose we're looking for all witnesses involving some fixed element B in the middle set. This can immediately be rephrased as an intersection problem where we take set A, shifted all the elements by B, and ask does that intersect C or not. Okay, so threesome, if you just write it the right way, looks exactly like some kind of offline set intersection thing, except the sets get shifted by these numerical values. Okay, so this is a wonderful trick from Mihai. If you're trying to simulate a shifted set intersection, it's useful to look at, these are integers, so you can just look at the bit representation of the actual numbers A, B, and C. And this is equivalent to checking whether A shifted by the higher order bits of B is equal to C shifted by the low order bits of B. Okay, so the number of shifts here is basically square root of the number of possible shifts if you just look at A plus B equals C. Okay, so the algorithm is basically as follows. For each B, we're going to check if A shifted up by the higher order bits of B intersects C shifted down by the lower order bits of B. And if it is, then we know that we've found a threesome witness. And if it isn't, then we move on to the next B. Okay, so this is clearly a set disjointness problem. The number of sets is 2 times the square root of the universe. I didn't say what the universe was, so it could be big, so this could be really awful. The total size of all the sets is n times the square root of the universe, which is way too big. You know, if you're looking for an n squared running time, U doesn't have to be that big before this is already exceeding your budget. And the number of disjointness queries is n, 1 for each element in B. So the way we're going to fix this is use hashing. So the universe is too big and n is too big. So we're going to use hashing to basically fix both of those problems, make the universe smaller and make set sizes smaller. Okay, so we need hashing for load value. So this was introduced in Barandamen in Petrovsky. So we'll call a a distribution over hash functions h c universal if the probability of getting a collision between h of x and h of y is c times what it should be. So the range of the function is r, and it should be 1 over r, but it might be as much as c times 1 over r. Okay. So suppose we take a C universal hash function, and we have a set of elements A, and we hash A into buckets as follows. Bucket I is everything with hash value I. Okay. So we expect to see n over r elements in a bucket, and if it has 3 n over r elements, we'll call it overfull. And overfull is generally bad, so think of this as a bad event. And the theorem from Barandman and Petrovsky is that if h is one universal, that is, it is exactly as good as a random function in terms of bounding the probability of collisions, then the expected number of elements in overfull buckets is on the order of the number of buckets. This is weaker than what you'd expect via total randomness, via Chernoff bounds, for example, but it's still very strong. Okay, and I want to illustrate exactly why it's strong by showing that this one universality thing right here is actually really critical to the proof, and that the whole thing unravels if you don't have one universality. Okay, so, and the claim is that this isn't true if you allow any deviation whatsoever from one universality. So here's a counterexample. We'll pick a hash function h from the following distribution. H of A is with epsilon probability mapped to an epsilon over 4 fraction of the range, and with 1 minus epsilon probability, it's mapped to the rest of the range, uniformly at random. So pictorially, we're just taking an epsilon fraction of the universe and compressing it down to epsilon over 4 in the range, and taking the rest and compressing it down to the rest of the range, or expanding it out into the rest of the range. Okay, so it's fairly easy to verify two things. This doesn't screw up the collision probability that much. It's still 1 plus something on the order of epsilon universal. And because that the expected bucket size for the buckets in this part of the range is 4 times what you would expect, nearly everything in these buckets is going to be in overfull buckets. So an epsilon fraction of the elements in the set get mapped down to something where they are almost certainly going to be in overfull buckets. Okay, so epsilon n and r are unrelated parameters. There's no way to bound one in terms of the other. So this theorem basically falls apart unless you have strict one universality. Okay, so hashing for universe reduction. Hashing for load balancing is going to, this is one use of hashing. Hashing for universe reduction, we're going to need a little bit slightly different properties. Because generally, when you think of hashing something, you think of just screwing up the data, right? So we're looking for threesome witnesses. If you hash the input data, you're going to screw up the data and destroy the property of being a threesome witness. So what we need now is hash functions that, in addition to having nice properties like one universality, are also linear, so they preserve threesome witnesses. So we'll call h linear if h of x plus h of y equals h of x plus y for any xy. And linear functions are too hard to come by. So we'll settle for this definition of almost linear. So we'll say h is almost linear if you have linearity, and you may be off by linearity by a term that depends on the hash function you chose, but not the inputs. And you may be off by that by some additive amount. So the whole point of this is that h of x plus h of y is one of a constant number of possible values depending on h of x plus y. Okay, so here's a first try. This hash function was suggested in Barandman, Petrovsky, and later in Petrovsky because it seems to fit all the bills. It's clearly almost linear. So what is this function actually doing? If you write this out in C notation, maybe it looks a little bit more easy to digest, but you pick a random odd integer a, you multiply that by the thing you're hashing, and that creates a 2-word output, mod 2 to the w. W is the word size, so this retains the lower order word, and then you shift out all but the r higher order bits of the lower order word. Okay, and that's your hash value. So except for this part right here, it's linear, and all you're doing here is throwing away lower order bits. So you get almost linear where C is 0, and the 0 and 1 here just is there because when you throw away lower order bits and you add two numbers, you might be losing a carry. And that's what this 1 is the lost carry. Okay. It's a first try because it doesn't work. So this function is not one universal, it's two universal. And therefore you can't apply the load balancing lemma given this function. Maybe you can, but you'd have to prove it, on an ad hoc basis. You can't say because it's two universal, it's good enough. Two universality is not in and of itself good enough. Okay, so the second try is not that much different. So instead of saying AX, you just say AX plus B. A and B are random W bit words. Okay. So the B here is basically going to affect the choice of CH. Right. Okay. So Diesfelbinger in the 90s showed that this is pairwise independent. It's not just one universal, but it's pairwise independent, and it's also one universal because of that. And we're going to use both of these properties. One universality for the load balancing lemma, and pairwise independence for other things. So when I say a hash function, I mean one from this class where A and B are drawn uniformly at random. Okay, so remember the setup. We have a fixed B in the B set, and we're looking for an A in the A set and a C in the C set that form a threesome witness. And we want to reduce this to some kind of set disjointness query. So the first thing that we do is we pick a hash function H, and we hash sets A and C into R buckets. R is, we get to choose R, and we hash them into R buckets using the bucketing described before. Okay, so assume none of these buckets are over full. We don't care about that for this talk. Okay, so I'm going to also assume that H is completely linear because all this stuff about approximate linearity is just noise. It doesn't interfere with what's actually going on. So assume that H is perfectly linear. H of A plus H of B is always exactly H of A plus B. So if A, B, and C form a threesome witness, then their hash values also form a threesome witness. So we'll call the bucket that A got hashed into bucket I, and the bucket that C got hashed into bucket J. So to solve threesome, we just have a quick set of nested loops here. So for every possible value of B, we pick every possible value of the bucket that A could have been hashed into, AI. So once you fix B, you get H of B. Once you fix I, J is a function of those two. So you immediately get J. And now you can reduce the question, is there a threesome witness involving B, to the set intersection query. For each I, does AI shifted by B intersect CJ? And if it does, then you've found a threesome witness. And if it doesn't, then there is no threesome witness involving B. Okay, so here we have a type of intersection query that we'd like to support. So here's the observation for why this is going to be efficient. So AI is a bucket, CJ is a bucket, and let's say they're not overfull, so they each have something on the order of n over r elements in them. Okay. So with the birthday non-paradox in mind, we'll pick a new almost linear hash function h prime. It has to be, independent of h that we picked before to do the actual bucketing. We'll pick a new function h prime that maps whatever the universe is down to the size of these buckets squared. Okay, so this is roughly equivalent to asking a question, under the projection of h prime, does the bucket AI shifted by B intersect the bucket CJ? Okay, now because, this is almost equivalent, right? Because you could get something that looks like a threesome witness here. If you see an intersection under these two sets, it doesn't necessarily translate into a witness in the original problem. Okay, and then of course we can apply the same trick by moving the higher order bits of h prime of b and the lower order bits of h prime of b into separate offsets on these sets. So remember that the higher order bits and the lower order bits is the number of different shifts here is square root of the universe, but the universe is not U anymore. It's the size of these buckets squared. So the number of shifts that we're talking about handling is only n over r. Okay, so if there was no threesome witness involving B in these two sets, in AI and CJ, then these sets started off as disjoint, and under this this pairwise independent function h prime, they stay disjoint with constant probability because of this birthday non-paradox. So if we want to have a higher confidence, when the answer is yes here that there is a witness, and we want to have higher confidence that this answer is correct, we'll just repeat this test log n independent times with different h prime values. And if all log n of them say yes, there's an intersection here, then we actually go and look for an intersection. And we either find a false positive with negligible probability, or we find an actual threesome witness and halt. Okay, so roughly speaking, this is what we've done. We've created a set disjointness instance from a threesome instance where there's n log n sets regardless of what number of buckets we use. So we have r buckets, n over r shifts, and log n different hash functions. And there's, so it's n log n independent of r. The total size of all sets is roughly n squared over r. And the total number of queries is roughly n times r. So the number of queries was, we had to check every value of b, and we had to check every value of where a got, which bucket a got hashed into. And that's each of those corresponds to a separate set disjointness instance, set disjointness query. Okay, so in this reduction, so in Mihai's reduction, epsilon was bounded between 1/2 and 1. And in this reduction, let's call the size of the number of buckets n to the gamma. Gamma is unrestrained, so gamma can be anywhere between 0 and 1, and we don't run into any trouble. Okay, so if you believe the threesome, the threesome conjecture that you need n squared time to solve the threesome instance, that says that figuring out answering these NR disjointness queries also must take little n squared time. Okay, and if you run through this reduction with a different hypothesis, you'll see that nothing, you still get non-trivial results if the complexity of threesome is n to some exponent that's strictly greater than 1.5. And at 1.5, basically everything just vanishes and you get nothing. Okay, so here's some interesting implications for online set disjointness. So that we reduce it to offline set disjointness. One way you can solve offline set disjointness is with an online set disjointness algorithm that pre-processes the sets in advance and then online answers queries. So it doesn't know the queries in advance, so we're just getting to a harder problem. But this is useful because A, these data structures exist. This basically, any search engine that answers 2 query word searches is doing exactly this, so it's well motivated. But it also lets us disentangle pre-processing costs from query costs and see what the reductions are actually showing. So we have 2 to the minus n to the 2 minus gamma size of all of our sets, and roughly n to the 1 plus gamma queries. So that's kind of the this is what gamma controls here. So here's some interesting implications. So if you send gamma close to 0, not equal to 0, but just close to 0, and you want a data structure that has near linear time preprocessing, this lower bound says that you need square root of n time query time per disjointness query. If you send gamma close to 1 and you demand near constant query time, then you need near quadratic preprocessing time. Okay, so if you go through Mihai's reductions and look at the same points on the trade-off curve, if you needed near linear time preprocessing in his reduction, you would get n to the 1/3 lower bound for query, and if you needed near constant query times, you'd get n to the 4/3 lower bound for preprocessing. Okay, so this second one right here, which I think is pretty relevant, is if you want constant query time, you need quadratic preprocessing time. This is basically tight. Getting quadratic preprocessing time and constant query time, just doing the dumb brute force thing, is basically an optimal algorithm. You're not gonna improve this exponent here too by any at all. And the first trade-off here is not really tight, but it's getting there. So the best data structures, if you want square root of n query time, you need about n to the 1.5 preprocessing time instead of near linear time, but that's basically the state of affairs right now. Okay. So there are some limitations to this reduction from threesome to set disjointness. One reason set disjointness is a really useful problem is because so many other problems, particularly graph problems, can be expressed as set disjointness. You can, these reductions are so easy they're almost not, worth enumerating anymore. So, but one of the problems is that when you take a set disjointness instance and you represent it as a graph, roughly speaking, the size of the sets gets translated into a number of edges. And the number of vertices is you get a constant number of vertices per set and per universe element. So you pay for the sets and the universe elements in vertices. And here we had n log n vertices representing sets, and we'll have something like n to the 2 minus 2 gamma vertices representing the universe. So if you pick gamma to be not too big, then this is a lot of vertices. So the densest graphs you could possibly create using this type of reduction is you pick gamma equals 1/2, and you get roughly n log n vertices and n to the 3/2 edges. And you can't create a denser graph using this reduction. So this is sort of disappointing, but I feel like this is sort of an intrinsic barrier with this line of thinking. Because if you ask a set disjointness query, you need the answer to be informative. You need, zero, a non-intersecting set to mean one thing and an intersecting set to mean something else. So if you're creating basically instances generated at random, the universe size in ours is always the average set size squared. And if you try to make the universe smaller, you're not going to get anything informative out of these set intersection queries because they're always going to intersect. There's nothing going to be and there's going to be no information coming out of these set intersection queries. So this is sort of an intrinsic barrier. The way we get around it is just switching the problem. We don't really fix this directly. So here is a way around it. We change the problem. So instead of the data structure, the set disjointness data structure just saying yes or no, these things intersect or don't, we're going to look at a slightly different problem, set intersection. And it's just like set disjointness, remember, but where you're obliged to enumerate everything in the intersection. So the reduction is exactly the same. We still use h to hash into buckets. And now we choose h prime to be, instead of the average number of things in a bucket squared as the new universe, we pick it to be the average number of things in a bucket times n to the delta, where delta is a new parameter. So if you make delta kind of smallish, then you're going to create instances where sets intersect by a lot, and all the points in the intersection are going to be informative. So now the reduction says when you have to answer in a set intersection query, let's say it's A hashed, shifted by some higher order bits of B, et cetera, report everything in this intersection. And every element in this intersection is going to correspond to a false positive, which you can quickly check and throw away, or an actual threesome witness. And you have to go through everything in the intersection to figure out which one's which. Okay, so the expected total size of the output of all of these intersection queries is going to be n to the 2 minus delta, which just says that you need about n to the delta time per reporting operation without violating the threesome conjecture. Okay, and if you look at how this reduction works, you can create very, very dense instances by making delta very close to 0, but not equal 0, and gamma very close to 1/3. So under this type of parameterization, what you do is you basically create a graph with roughly n to the 2/3 vertices and n to the 4/3 edges, and it's nearly complete. And with different parameterizations, you can create graphs of almost any density. Okay. So let me just give sort of one point on this trade-off curve for set intersection and see what kind of implications this lower bound has. So suppose we have a set intersection data structure, so it actually reports the intersection of two sets. And we have preprocessing time TP, query time TQ. So when we ask a query, it's going to take TQ time regardless of what the set intersection looks like. And for each element in the output, we're allowed TR time. So TR is the reporting time. So if we have some data structure and its running time is characterized by these three things, then we have this lower bound. This is very ugly looking because we have two independent levers that we're controlling. We have the gamma lever and the delta lever, and they both control different things. So this is not really an easy trade-off to get a handle on except by fiddling with it. So you can just, pick some random thing. So let's say, hypothetically, we have a data structure whose preprocessing time is less than n to the 4/3, whose reporting time is near constant. What this lower bound implies, if you send gamma and delta close to 0, is that you need at least n to the 2/3 query time, even though the output of the set intersection queries is less than n to the 2/3. Okay, and this is actually 1 point on a tight trade-off curve. So there is a data structure, with a trade-off curve that actually meets this particular point and lots of other points. Okay. Okay. So I'll show one more reduction of how you get from set disjointness to a graph problem, which will maybe be a good segue into Tzvi's talk. So a lot of the other implications that we get from this is new bounds on the complexity of reporting triangles, and C's going to talk about that. But I just wanted to talk about another thing: dynamic maximum matching. So here the problem is you maintain some dynamic graph, and you get to add vertices and edges, and those are the incremental operations, and delete vertices and edges, and those are the decremental operations. So it's pretty easy to show that if you literally had to maintain in memory an explicit representation of a maximum matching, that you can't do this in less than linear time. So we're going to weaken this slightly and just say after each operation, we just want to know the size of a maximum matching, which there's no obvious bottleneck for this type of query. Okay, so Abood and Williams gave lower bounds in this problem via some stepping stones from other problems, and you can express their lower bound in terms of the number of edges or the number of vertices, but for reasons that will be clear later on, I'm going to express their lower bound in terms of number of vertices. So they showed that if your data structure is amortized and fully dynamic, you need square root of n time per number of vertices, square root of number of vertices per operation, and if your data structure has worst case guarantees but is only incremental, you get the same lower bound. It's the same reduction, but there's two ways to kind of, phrase it in terms of amortized, fully dynamic, and worst case incremental. And it doesn't really seem possible to kind of combine the best of both worlds in these reductions and end up with this 1/2 exponent. So here I just want to show a cute little technique for getting some kind of non-trivial exponent here in the amortized incremental universe. So this is the basic setup. There's going to be 3 blobs. Blobs represent the following things. So remember, we're trying to simulate with a matching instance the set intersection queries where we look at a set derived from A, intersect a set derived from C, and see if they're empty or not. So these blobs will contain vertices that represent sets derived from A. This blob will have things derived from C, and this blob here will be things derived from the universe. So for each universe element U, we'll create 2 vertices and an edge between them. For each set derived from A, we'll create 2 sets, two vertices A and A prime with an edge between them. And if U is in A prime, then we'll connect these 2 vertices by an edge. And we'll do something symmetric for the C side. For each set little c, we'll create 2 vertices C and C prime, and connect C to UC if the element U is in the set C. Okay, so if you stare at this graph, you'll see that it has a unique perfect matching. You just match every vertex with its partner, and that's the only perfect matching. So it looks like this. So if you want to answer a set disjointness query, you just come along and add a new edge from a new vertex x to a prime, a new edge from a new vertex y to c prime, and if the size of the maximum matching grows after you add these two edges, then you know that sets A and C intersect. You have to stare at it for a little, and then you believe it. So, if they intersect, you have a very short augmenting path, and if they don't intersect, it's not like there's some long contrived augmenting path. There is no augmenting path if they don't intersect. Okay, so that's basically how you answer exactly one set disjointness query, and now what you have to do is delete these edges that you just inserted so you can move on and ask the second set disjointness query and the third and so forth. So you need a way to do deletions. So if you're in the amortized incremental model, there is no deletion operation, so you don't really have a direct way to delete these edges. Okay, so there's two ways that you can functionally delete edges in this problem, and we'll use both of them. So to functionally delete these edges, what you could do is just basically every time that these add edge and add vertex operations are doing their thing, you just record all the memory addresses that they look at and the values that were there before. And when you're done adding the edges from x and y, you just roll back the data structure to the state it was in before they were there, and then you can start from there and then do the next one. So if you have worst case guarantees, a rollback, you know how much a rollback costs because there was a worst case guarantee and you could roll back the operations in worst case time. But if you have an amortized guarantee, rollbacks don't work. You could have a very expensive operation, and rolling it back is not a good idea. Okay, so that's a general way to basically do deletes. A specific way to do deletes that's only relevant to the matching problem, as far as I can tell, is you can simulate deletes by adding more vertices and more edges. If you just add another vertex y prime and connect it to y and x prime, then you again arrive at a graph where it has a unique perfect matching, where every vertex is matched with its partner. Okay, and you functionally deleted those two edges. So basically, figuring out exactly what this exponent is kind of tedious, but basically you divide the operations, the set disjointness queries into cheap and expensive. If it's cheap, meaning it came in under its amortized budget, then you undo the inserts with a memory rollback. And if it's expensive, then you undo the inserts with more inserts, and you grow the number of vertices. So when you grow the number of vertices, you change the threshold for what cheap and expensive is. And figuring out exactly how big this graph can get is kind of tedious because the graph starts out with, you inserted so many edges and vertices at the beginning, it starts out with this possibly enormous reservoir of potential that it can spend down in the future with amortized operations. So this vast reservoir of potential at the beginning is basically going to influence how many vertices end up in the graph eventually, which blah, 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 blah. So this exponent is like square root of 17 minus 1 over 8. Okay. So, how much more time do I have? Does time exists? No. 2 minutes. Okay. So here's an open problem. I'm curious to know the exact relationship between convolution threesome and threesome. So they're either Mihai's reductions show they are both similarly subquadratic, meaning they're both off by log factors, or off by polynomial factors, or off by something in between. But that's the highest level of granularity you can really say. So it's easy to show convolution threesome is reducible to threesome. That's easy. A new result we have is that threesome is reducible to log n instances of convolution threesome of the same size. So the gap here is no more than log n, and this is randomized and it uses hashing, et cetera, so it's only for integers. So getting rid of the log n is something, and also just identifying any type of relationship between threesome and convolution threesome over the reals. So this is an issue that actually shows up in a lot of reductions, which is that when you're hopping between problems, sometimes you need the reductions between problems actually depend on some bounded precision in the integer inputs because you're doing some kind of search over the integer inputs. Okay, so I have no idea whether threesome and convolution threesome are related over the reals. Okay, here's another interesting open problem. So Williams and Williams showed that convolution threesome, even the real version of it, is reducible to square root of n instances of the zero-weight triangle problem on square root of n nodes. And this has very interesting implications. It says that either one of these two things is they're either one is going to be cubic and the other is quadratic, or they're both going to be subcubic and subquadratic. And separately, integer APSP is also reducible to zero-weight triangle. Okay, and so this reduction just fiddles with the numbers in some completely linear way. Okay, and it works with reals. It doesn't matter. This reduction is actually looking at the bit representation of the weights. So this is not the reduction is not quite in the same flavor as this, but it's very similar. Okay, so the fact that this zero-weight triangle problem exists and is related to these other two things says that there's some moral connection between these two, and it would be nice if you could have a really explicit, tangible connection between convolution threesome and APSP. Okay, Ellie couldn't be here, but he's busy.
Any questions for Seth?
Yes?
Somewhere in your talk you mentioned that there was a reduction from, I think it was threesome to graph problems.
Yeah.
And that it was unfortunate that the number of edges is at most n to the 3/2.
Yeah.
Why is that unfortunate?
Well, for example, a lot of problems have this phenomenon where you see mn running times that are, as far as we know, optimal up into a certain density, and then suddenly fast matrix multiplication becomes a realistic technique, and then you see a completely different spectrum of running times after some density. So the fact that we can only create some graphs of some densities means that when we say an algorithm's optimal, we mean, only for sparse instances. And what we wanted to do was say something really strong and say, both the algebraic algorithms for dense instances and the combinatorial ones for sparse instances are optimal. And that's why we needed to create dense ones is to think about, basically lower bounds for algorithmic techniques that only kick in at certain densities.
But it's still a useful result.
Oh, it's a nice range, yeah, but.
An additional step is.
Right, yeah. I'm not saying that dense graphs show up in nature a lot, but, I don't think they do, but. Cute kid, huh?